Okay, much better. Okay, thank you for coming for this presentation. So I will talk about something very specific, maybe a little bit different from all the previous presentation. So I'm Sir Stinguish, I'm an associate professor, and I'm working in a research unit called UMISCO. It's located in mostly in France. And I will talk about a domain-specific language for epidemiologists called Kendrick. So this work is mainly the work of my PhD student, May Hein. So normally she will defend her PhD soon, so she couldn't attend the conference, the workshop. Okay, so first of all, I would like to give you some context, because I think it's very important to understand why we are doing that. So I'm working in an international research unit that is split in many places around the world. So we are in Paris, but also in Morocco, and Senegal, in Cameroon, and in Vietnam. So most of the time, because we are working with developing countries, we are the people from the research team, the French people, they are moving and spend some time in these countries. So, for example, I spent 4 years in Vietnam from 2008 to 2012, and recently I spent 2 months in Cameroon. So we are working on complex systems from the point of view of the mathematicians and the computer science. And we try to apply what we are doing on problems that are coming from developing countries. So what we are doing is basically we are doing models of systems that are basically biological systems or human systems. So we represent this kind of system, this kind of complex system with a simplified representation called model. And after that we are doing simulation analysis of these models in order to interpret them or analyze them. And we are mostly working on these three key application domains: emerging diseases, climate change, and natural resources. So recently I spent 2 months in Cameroon, in Yaoundé, so hopefully Stéphane come a few months before, and he has done a lecture about Pharaoh, so it was very easy for me to work with this guy that you see on the picture, because they have already some backgrounds about Pharaoh, and we are now trying to push them to use Pharaoh for their research activities. So we are working mainly on two main applications, so the epidemiological surveillance systems and the modeling and simulation of epidemiology models. So just to give you an overview of what we are doing, we are working mostly on two applications. One is called EPICAM. It's a model-driven engineering platform for generating epidemiological surveillance systems. So at the moment it's written in Java, but we want to move it maybe soon in Cameroon. So this is a software that is used to collect information around Cameroon, and it's already deployed on 25 sites around the country. And we are also working on this platform for doing modeling and analysis of epidemiological systems. And the idea is that to help this kind of expert to build more easily and analyze more easily what their models do. And we want to build tools that are much more easily to use than the existing tools. So, what is epidemiology modeling? So I don't have time, and I guess you are not really interested in all the mathematical details about these kind of models, but basically we are the epidemiologists are building these kind of models to study the speed of the disease inside a population. By population, it's not only human population, but it could be also animals like birds or flies or mosquitoes. And most of these people, they are using compartmental mathematical models. So this kind of models has been introduced in the beginning of the 19th centuries by these two guys. So it's Kendrick and Carmack. So you now understand why we called our tool Kendrick. So just to remind the name of one of these two guys that introduced this kind of models. So this is an example of a model that they are using. So basically you have a population of individuals, and you split this population in some compartments. So for example, here you have 5 compartments. So each individual is one as one of these status. So you have susceptibles. The first one is the people who are not infected by a disease. After that, you are infected, so you are higher. And you have three different possibilities. You can be recovered, R, or put in quarantine, Q, or dead. So it's the end of the story. And you see on the transition of this kind of models, you have rates. So it's a stochastic kind of models. So you can do simulation after that. And so they are basically, the epidemiologic, they are expressing the model like that, and after that they are doing analysis and simulation. So I will talk about the most simple model, it's the SIR model. It's a model of the missile disease. So you have three compartments, susceptibles, infected, and recovered. And in fact, you can see a graphical representation of this kind of models, but in fact, it's completely equivalent to a set of ordinary differential equations that you see here. Okay, it's the same system. And if you do a simulation, you have this kind of graph. And for example, here, I guess the green are the infected. And you see that there is a peak of epidemic. There is an epidemic peak at one point. It's very usual in the disease. At one point you have a peak, and after the peak decrease. So after the people have built models, they want to do simulation. So there's many ways to do simulation. I don't have time to explain all the details, but basically there are three different ways. You can do simulation at the population level. So you are using ODE solvers. So because you have a large population, there is no noise, no stochastic aspect. So you are just using a solver, ODE solvers like Runge-Kutta. You can do, if you have the population that is not that large, you can use individual level simulation, and you are using stochastic simulations. That means that you have to deal with the noise. And if you have lots of computation power, you can also do agent-based level set. That means that you represent each individual by different entities in a computer. So, when the epidemiologists are building models, they have to deal with lots of concerns, different concerns, okay? So I have made a list of some of them here, and I will explain to you some of them more in detail. So for example, you have some disease, there is a propagation between multiple hosts, okay? So for example, here is a plague disease, so you see all the interaction between the different species, you have flea, you have rodents, you have domestic animals, you have the humans, so you have to deal with this kind of models if you want to build a tool to do simulation of in this domain. After that, another concern is that most of the disease, there is lots of strains. So for example, this is the flu, influenza, and you see all these strains, so there is some little variance between the different strains, and you have to represent this variability at some point, and you have to deal with that also. Another problem that you have to deal with is the spatial concerns, because the simulation are done at the level of a region or countries or continent, for example, like this one. It's a picture of the propagation of the malaria. So the first model that you have seen, the SIR, it's very simple, there is no space. But if you want to have more elaborate models, you need to take into account this kind of concerns, spatial concerns. And the last one is the control strategies. Because you want to save some lives at some point, so you can implement in your model some control strategies like quarantine or vaccination strategies, and you can do simulation in order to see if this kind of strategy will have some effects on the disease. Okay, so how our epidemiologists are building their models? Okay, let's start with these models. It's SIRS models, very easy one, and it's a model of the avian flu. Okay? Okay, so the people, they have just put some equation like that. After that, they implement the model. Do you know the language? MATLAB, yes. And they do simulation, analysis, etc. So it works. After that, they want to improve the model, so they take the first model and they add some two concerns here. They want to study not only one species, but animals and birds, okay? And they want to do special models with different patch. So you see here, S is the species and P is a patch. So this is the same model, but with much more details. And after that, they implement something like that in the MATLAB, but this is a mess. Okay, it's very difficult because they have to modify the previous version of the program, and you see the modification in yellow here. So all the concern, and this is a very simple model, okay? All the concerns are scattered around the code. The concerns are tangled. It's not modular, it's not reusable, okay? So, and the people that are doing that since decades, okay? So we have to propose something that is much better than this solution. So we want to promote in our language separation of concerns, okay? So we want to decompose models that are highly coupled monolithic models into a modular set of concerns. So we have proposed some solution to define the concerns with as few as dependency as possible and to combine these concerns as freely as possible. So our solution is to provide, so I don't want to enter into detail because it's a little bit complex, but we provide a mathematical meta-model that is based on stochastic automata. And we provide some tools on this automata, so we are able to compose models with a tensor sum, and we are able to transform some console to modify the automata. So there is a lot of magic mathematical tricks behind, but it works. So for example, this is a very simple example. You have SIR, so the missile, for example. You have a spatial model with Paris and Prague. Okay, so you have people who are moving from Paris to Prague, like some French people who are coming to this conference. And you are doing the tensor product of this, and you obtain a much more complex automata, and you can do that many times. So basically, what you are doing is, at the end, you have a very big automata that you want to do simulation with this automata. So we implement a language called Kendrick. So it's an embedded DSL in Faro that allows to do that. It's completely open source, it's available, it's MIT open source. And this is what we have done. So this is the result. So with a kind of small talk syntax, you are you can express your model in very simple ways. So for example, here you have a SIR, the fact that you are moving from one city to another city, and you can compose these two concerns and initialize some of the parameters and do a simulation. Okay, so maybe it's better with a demo now. I don't know how many time I have still.
6 minutes.
Okay, plenty of time. Okay. Here. Can you hear me? It's okay?
Yeah.
It's okay. Okay. So, first of all, we start with the missile model. So maybe I will enhance a little bit the fonts. Here, this is the small talk code because we have some problem with the DSL at the moment, so I prefer to skip it. So, but basically, this is the same. Huh? The DSL just add a nice syntax on top of small talk. So we have a very simple model here, SEIR. It's a missile model. So what I can do, I can execute this model. So basically what I have, it's a result with a different status here. So you see the peak here of exposed people, and after that the peak of infectious people. And you can also have access to the graph of the models. Okay? Here the graph is very simple. But for more elaborate models, it could be a very huge graph. Another example. So this one is a model for that. In fact, we are interested by doing a simulation at the individual level. So we want to represent every individual, so we are using here 100 people, and we are propagating a disease. It's very simple, it's SIR disease between them. Okay, so we execute the code. It takes a bit more time because there is 100 people to take into account. Yeah, because it's pretty, everything is done in pure Smalltalk, but there is no acceleration. So basically you have the same kind of results. Here you see the peak of the disease, and here what you see, this nice Russell visualization, is that the network between the individual. So there's a contact network. Okay, so you see each individual here with the status. So green is susceptible, red is infected, and blue are recovered people. Okay, and you see every time there is a link, there was a contact at one time between the two people. Okay, and we can have a look to the okay, can have a look to the. So this is an SIR model. So you see the SIR, and because there is 100 individual, you have something like that. Okay. So each individual has a SIR model. Okay. And the last demo, it's an Ebola model that we have done. So the idea is to do a simulation between different countries. If you remember, there was a big peak of Ebola last year or 2 years ago between some African countries, thank you. Guinea, Sierra Leone, Nigeria, and Senegal, and Niger. So we want to do a simulation that to reproduce some of the behavior of this propagation. So it takes a lot of time. 1 or 2 minutes, something like that. So if you have questions, we can start the question right now during the presentation.
So for how many people or parameters have you run it at once? So what's the largest population?
It depends on what kind of simulation you are doing. If you have a very large population with 1 million people, and you can do deterministic simulation, and it's very efficient. After that, if you want to have more details about what you want to do, you use stochastic simulation, and it's very costly. So I guess if maybe in the future we would have to use some external library written in C or something like that. It's already possible to generate, when your model is working well, you can generate a C version of your model and run it externally. So it's possible. So let's have a look to the results. So this is the just plot here the infectious status of some countries here. Okay, and thanks to Russell, we have also map representation like that very easily. So we can see that there was a different variation of infection between the different countries here. So the red is not the same red, and we can have a look to the model. So this is the model of the disease, something like that. In fact, this is the 5 countries, and every country is an SIR model. Okay, so let's go back to the presentation, and so if you want to try Kendrick, it's very easy. You just have to buy the Agile Visualization book. There is a chapter about it. And you can download the Moose 6.0 image and know which you go. Thank you, Alex, not here. Thank you, Alex, for this opportunity to write a chapter inside your book. There was lots of participants, and I want to thank them all around the world. And so, just the conclusion. So we have built a domain-specific language for epidemiology. So the idea is to separate the concerns that you are usually find in these kind of models. And we In fact, we are relying a lot on the Faro community because we are using a lot of tools. We are using Polymath for doing all the computation. We are using Russell. We are using Petit Parser to parse the equations. We are using Smalltalk CI for the project. So we are reusing a lot of tools. And this is some of the ongoing work we are doing. We want to do a GPU implementation in order to solve some performance issues also. And we also want to do some real experiment with people who are not computer scientists, because at the moment we have only used this tool inside the team with people who are half mathematicians, half computer scientists. So next year we want to be able to put this kind of tools in the hand of epidemiologists to see if they can use it or not. Okay, thank you. More questions?